So this is going to be a guide going over a thermodynamic problem with compressibility. It also has ideal gas equation, and there's some steam table stuff in here. So to get started, the problem is determine the specific volume of superheated water vapor at 15 megapascals and 350 degrees Celsius using the ideal gas equation, generalized compressibility chart, and finally steam tables. And as we know, steam is not super ideal at these conditions. So then we're going to find the percent error based off the steam tables, which should be the most accurate. So getting started in the first part A here, we have PV, pressure times specific volume, is equal to the gas constant times temperature. So if we plug in, first we're going to rearrange. We're going to set specific volume equal to gas constant times temperature over pressure. Then we have, plug in our numbers here. We get 0.4615 kilojoules per kilogram Kelvin. This is the gas constant for steam here, times 623. Make sure you're always using Kelvin. With the ideal gas equation, you don't want to be using Celsius here, so just add 273. And this is all over 15,000 kilopascals. So here we get a specific volume of 0.01917 meters cubed per kilogram. And then if we do our percent error calculation, this is going to be, we'll get the actual value later, but it's the value we got minus the actual value, all divided by the actual value again. So this simplifies down here to 0.669 or 66.9% error. So now we move on to part B. We have, this is with the generalized compressibility chart. We get that the pressure reduced is the pressure that we actually have divided by the critical pressure, which is 15 megapascals divided by 22.6 megapascals. Again, we're gonna want to find the pressure reduced and the temperature reduced. What this does is it helps us look at the compressibility chart, and then from there we're going to get the compressibility factor, from which we can determine the specific volume. So yeah, we have our relative pressure there, 0.6799 or 0.68. The temperature reduced, same thing here. It's our actual temperature, 623 degrees Kelvin, divided by the critical temperature of steam, 647.1 degrees Kelvin. And this simplifies to 0.936. So if we go to a generalized compressibility chart, you can see here we have our temperature reduced lines, and we also have our pressure reduced is down here. We said our reduced pressure is 0.68, so that's going to be right there. And we can see the temperature reduced is 0.96. So going here, you can see this is 0.95. And if we follow this here to 0.68, we get a compressibility factor of just about 0.65. And our compressibility factor is PV over RT. So if we go back here, there's our compressibility factor. It equals PV divided by RT. So we're just going to rearrange this. Our specific volume now equals compressibility times RT divided by P, which is equal to the 0.65 we got, times 0.4615, the gas constant for steam, times 623 degrees Kelvin, and the whole thing is divided by 15,000 kilopascals, which finally gives us a specific volume of 0.012459 meters cubed per kilogram. We do the same percent error calculation. We get the value we got minus the actual value divided by the actual value, which gives us 0.0851 or 8.51% error. So much closer than the last one. Now onto the last part, using steam tables. So first thing we're going to want to do here is we check the saturated water table at 15,000. So we go up here. Let's see, 15,000. We have a temperature of 342, and this is in degrees Celsius, and our value is 350. So our temperature is too high to be saturated, so it's superheated vapor. If we go here, looking for 15 megapascals at a temperature of 350. So our specific volume here is 0.011481. So if we go back here, you should see that we got specific volume here, 0.011481. And that's this entire problem.